Welcome to the class. In this class, we are going to discuss about the voltage regulation calculation of an alternator by using the MMF method and a Potier triangle method. First, let me see the MMF method of voltage regulation. In this method of voltage regulation, the armature reaction drop also will be considered as a armature leakage reactance drop. So, only one drop is available in an alternator, that is the armature reaction drop. To find the voltage regulation of alternator, in this method, it is also required the OC test as well as the SC test data. Suppose if you know the OC test data, then you take the field current on the x-axis, voltage on the y-axis. Make sure that this voltage is per phase voltage and note down the points on the graph sheet. If you line join all the points, you are getting the OCC of a alternator. When you are going to draw this graph on a graph sheet, take properly the scale for the voltage as well as the current on the x-axis. Same manner, take the field current on the x-axis and short circuit current on the y-axis. You noted the points and line join all the points, you are getting the SC characteristics of a alternator. The SC characteristics of alternator is a straight line which is passing through the origin. After drawing this graph, you have to find out the per phase induced voltage, that is V phase plus IA RA cos phi. IA is nothing but a stator current or the armature current where we have to find out the voltage regulation. Cos phi is nothing but the power factor where we have to calculate the voltage regulation. All these values are available in the numerical. You can find out the per phase induced voltage. Once you find the per phase induced voltage, the corresponding field current you have to find out from the OC curve. Suppose if you are getting 100 volts, now take the 100 volts on the y-axis, draw a one line parallel to the x-axis. It is intersecting the OCC at the point some x. From that point, you have to draw one vertical line to the x-axis parallel to the y-axis. It is intersecting the x-axis at one more point. That point is nothing but a field current corresponding to the E. Next, you have to find out the field current corresponding to the rated current of a SC test. The rated current of alternator we can find out because the rating of a alternator is given in the numerical. Corresponding that current, how much is the field current, that you have to calculate from the SC curve of a alternator. Similar to the how we have find out the field current corresponding to the voltage, same manner you have to find out the field current corresponding to the rated short circuit current. Value you have to take a IF2. Once we know the value of IF2 and IF1, then we can find out the IF0. IF0 is nothing but it is the field current corresponding to the induced voltage in alternator at no load. That is equal to square root of IF1 square plus IF2 square plus 2 IF1 IF2 cos 180 minus 90 plus or minus theta, where plus we are taking for the lagging power factor, minus we are taking for the leading power factor. Now, once you find the IF0, then you have to find out the corresponding voltage from the OCC of a alternator. This is IF0. The corresponding you have to draw one vertical line that is intersecting the OCC at a one point. From that point you have to draw one horizontal line. This is E0. Now the voltage regulation equal to E0 minus V by V into 100. That is given the percentage voltage regulation of a alternator. Now we are going to see the one numerical on the MMF method. The OC and SC test data of a 3-phase star connected 1000 kVA 1905 volts 50 Hz alternator has the following data. This is the OC test data, this is the SC test data, this is the field current. Now in this case, if you observe, means the SC test data is given only at a 30 amperes of current. One more important point what we have to observe is that the voltage is given for the line voltage. So when you are going to draw the graph, we require the phase voltage. So we are framing one more table where we consider only the phase voltages. There is no change in the short circuit current and there is no change in the field current. This is for the open circuit voltage per phase. How do you got this voltage means this reading divided by the root 3. Next we are finding the per phase rated voltage 19 0.05 divided by the root 3, we are getting the 1100 volts. Now the full load current equal to the power rating divided by the root 3 VL. Here it is given 1000 kVA, that we converted into the volt amperes into 1000, that gives the 303 amperes. Now by properly taking the scale, on the y-axis we have taken the open circuit voltage. In this case I have taken the 1 centimeter equal to 250 volts. Next on the x-axis I have taken the 1 centimeter equal to 10 amperes of field current. Locate the point and line join all the point, we are getting the OCC. Next we have to find out the E. E equal to V phase plus IA RA cos pi. In the numerical it is given that the power factor where you have to calculate, that is 0.8. IA value already calculated, RA value also given 0.2, and V phase also we calculated here 1100 volts. Substitute all the values, we are getting the 1148.5 volts. Now corresponding to this voltage, I have to find out the field current. So this voltage you have taken the y-axis, draw a horizontal line, and again you have to draw a vertical line from the intersection. We are getting the IF1. Nearly we are getting the IF1 is a 32 amperes. Next, rated short circuit current. The rated current of alternator 303 during the SC test, the reading is given at a 335 amperes. Now the short circuit current is proportional to the field current. From that relation, we are going to find out the IF2. How much is the field current at a 303 amperes of current. So 303 divided by 335 into 30, we are getting the 27 amperes. Next we are finding the IF naught. IF naught equal to square root of IF1 square plus IF2 square plus 2 IF1 IF2 cos 180 minus 90 plus or minus theta. In this problem, we have to calculate the voltage regulation at a 0.8 power factor lagging. So we have to consider here plus sign. Substitute all the values, we are getting the field current corresponding to the no load voltage 53.25 amperes. Now you locate the 53.25 amperes on the x-axis. So from this point you have to draw one vertical line that is intersecting the OCC. From that point, intersecting point, you have to draw one horizontal line that is intersecting the y-axis at one point. If you know that value means we are getting the 1540 volts. Now the voltage regulation equal to E naught minus V by V, that is into 100, we are getting the 38.18 degrees. All these values are approximate values only. Next, a 3-phase 1 MVA 600 volts 50 Hz alternator has a following OC and SC test on given below. The field current is given here, OC test data is given here. The numerical it is given only the OC test data, that is line to line voltage only. I have taken the per phase voltage because I wanted to draw the OC test. At a full load, 0 power factor, the field excitation requires a 42.5 amperes to produce a 6000 volts on a short circuit. 17 amperes of current is required to produce a rated current on a short circuit. RA value is given 0.1 ohm per phase. Find the full load voltage regulation at a 0.8 power factor. Take the proper scale. In this case, I have taken the scale for the y-axis 1 centimeter equal to 1000 volts, and on the x-axis I have taken the scale 1 centimeter equal to 5 amperes. Locate the points and line join all the points, we are getting the OCC of a alternator. This method is nothing but a zero power factor method or Potier triangle method. Potier triangle method, you draw a one line tangent to the OCC, that is nothing but a air line. Next, here the data is given in the problem. We have taken the one point A. A is nothing but a field current, comma, the voltage is 0 during the zero power factor method. 17 amperes of current is producing a rated current, but the voltage is 0. So I have taken this as a point A. The field current of 42.5 amperes to produce a voltage of 6000 volts, that I have taken the point B, that is 42.5 amperes, and here 6000 volts, this is line voltage divided by root 3, we are getting the 3461 volts. Now first you have to locate the point A. This is point A. Then you have to locate the point B. Because the field current is given, the voltage is given, so we can easily locate the point B on this graph. This is the point B. Now you have to measure the length OA, nothing but from this point to this point. The same length from point B, you have to draw parallel to the x-axis, that is BC. From the point C, you draw a one line parallel to the air line up to the OCC, that is the CD. Now you line join the D and B, that is DB. From the point D, I have to draw a one line perpendicular to the BC, that is nothing but a perpendicular line. This triangle is nothing but a Potier triangle. This Potier triangle is constant. We can move this triangle on the OCC to get the different points on a zero power factor of a alternator. Now if we line join this point and this point similar to the OCC, this line is nothing but a zero power factor line of a alternator. Now from the Potier triangle method, the length dm equal to, see here, the length dm is equal to the voltage drop in alternator due to the leakage reactance drop. In this case, we got the value of 500 volts, that is equal to IA into XL. If you find the value of full load current, then we can calculate the XL also. I have calculated the full load current, IA equal to the rating of alternator divided by the root 3 VL. We are getting the 96.227 amperes. You substitute this value in above equation, we are getting the XL equal to 5.135 ohms. Now we are going to find out the E01. E01 equal to V cos theta plus IRA whole square plus V sin theta plus or minus IA XL whole square. This voltage drop already we have taken from the Potier triangle method, that is 500 volts, that you have to substitute here. The remaining values, V is nothing but a per phase rated voltage, cos pi is nothing but the power factor where we have to calculate the voltage regulation, IA is nothing but a full load current, RA value also given. Substitute all the values, we are getting the 3789.2 volts. Now corresponding this voltage from the OCC, we are finding the field current, that we got the value of 35 amperes. Now the field current corresponding to the demagnetization effect in alternator, that also we can calculate from the Potier triangle. This length is nothing but the length BM is nothing but demagnetization ampere turns corresponding to the Potier triangle method. Approximately I have taken the 5.2 amperes. Once you draw that graph, you take the accurate values. IF naught equal to IF01 square plus IF02 square plus 2 IF1 IF2 cos 180 minus 90 plus or minus pi. Plus is for the lagging power factor, minus for the leading power factor. Substitute all the values, we are getting the IF naught. Once you know the IF naught, then you have to find out the E naught from the OCC curve. We are getting the 40 amperes. Once you got the 40 amperes of field current, you can go back to this graph. Look at the 40 amperes of current here on field, and you draw one vertical line that is intersecting the OCC. At the intersecting point, you have to draw one horizontal line. It gives the E naught. Nothing but a no load voltage induced in alternator. Voltage regulation of alternator equal to E naught minus V by V into 100. This is equal to 4000 minus 3461 by 3461. We are getting nearly 15.57%. So thank you very much. If you have any doubt, you can ask me directly, or you can ask in the comment box of YouTube channel, so that I am always welcome to answer all your questions.